A red dwarf star burns so dimly that from its surface you would barely cast a shadow at noon. Some of these stars are so faint they went undiscovered for centuries, even though they outnumber every other star combined. But what's even crazier is that dim is not the same as safe. Red dwarfs are the smallest true stars in the universe, often barely larger than Jupiter. Standing on a platform above one, you would see a sky the color of dried blood, dim enough to stare directly at the core without pain. But these stars erupt with flares thousands of times more powerful than anything our sun produces, capable of stripping the atmosphere off a nearby planet in a single burst. No warning, no build-up, just a wall of radiation crossing millions of kilometers in minutes. And this is where things become strange, because the next star on this list looks almost identical to our own sun, and that similarity is exactly what makes it unsettling. A yellow dwarf, the same class as the star you are orbiting right now, seems calm from a distance. Its surface churns at about 5,500 degrees Celsius, a temperature that turns iron to vapor instantly. If you stood close enough to see the texture of its surface, you would be looking at cells of plasma the size of countries, rising and collapsing every few minutes. No solid ground, no shadow, just a boiling ocean of light stretching in every direction. But the next star on this list burns so fiercely that yellow would look cold by comparison. Blue giants are among the hottest stars known to exist, some reaching surface temperatures beyond 30,000 degrees Celsius. They burn through their fuel so fast that many live only a few million years, a blink compared to the billions our own sun will last. Standing near one, ultraviolet light alone would be enough to break down the molecules in your body before heat ever became the issue. Discovered and cataloged extensively through spectral surveys throughout the 20th century, these stars remain some of the most short-lived objects in the galaxy. But here is the unsettling part. Burning fast does not always mean burning simple, and the next entry proves that scale can hide in the most unexpected places. A red giant tells a different story, one of expansion instead of intensity. When a star like our sun begins to run out of hydrogen, it swells outward, sometimes engulfing the orbits of its inner planets entirely. Its surface temperature actually drops as it grows, cooling to around 3,500 degrees Celsius, even as its total light output increases dramatically. If you stood on a platform at the edge of a red giant, the horizon would curve so gently it would feel almost flat, an entire sky filled edge to edge with dull orange fire. So what happens when a star runs out of room to expand? It collapses, and what comes next redefines the word small. A white dwarf is what remains after a star like our sun finishes its life, an ember about the size of Earth, but carrying nearly the mass of the sun that made it. A single teaspoon of its material would weigh several tons here on Earth. Standing on its surface is not really possible in any survivable sense, because gravity there is powerful enough to compress the very concept of standing into something meaningless. No atmosphere, no seasons, just a slow fade that will take longer than the current age of the universe to complete. If you've made it this far into the strangest bodies the cosmos has to offer, drop a like and subscribe, because the next entry does not fade quietly at all. A neutron star is what forms when a much larger star collapses under its own weight, crushing matter until protons and electrons merge into neutrons. A neutron star typically measures only about 20 kilometers across, yet holds more mass than our entire sun. Take a mountain range and compress it down to the size of a sugar cube, and you begin to approach the density found here. Standing on its surface is physically impossible. The gravity would flatten you instantly to a layer thinner than paper. But the next star on this list does something even a neutron star cannot, because it does not just crush matter, it warps the space around it into something almost alive. A magnetar is a neutron star with a magnetic field trillions of times stronger than Earth's. Some magnetars can distort atoms from thousands of kilometers away, pulling electron clouds into thin, elongated shapes long before anything solid ever gets close. Discovered as a distinct class of object in the 1990s through gamma-ray observations, magnetars remain some of the most magnetically extreme objects ever confirmed. Your body's chemistry, the very bonds holding your cells together, would begin to fail before you ever reached the surface. No pain in the traditional sense, no impact, just an unraveling at the level of atoms. And that leaves us with the question of what happens when a star does not collapse into a point, but almost does, and stops just short of the edge. A quark star is a hypothetical stage, even denser than a neutron star, theorized to exist in that narrow gap just before a star becomes something with no surface at all. We have never confirmed one directly, but the physics suggests matter here would break down even further than neutrons into a raw soup of quarks pressed together without space between them. If such a star exists, its surface gravity would be so extreme that light itself would bend visibly across short distances, curving the horizon into an unnatural bowl shape. But somehow, even this strange, unconfirmed object is not the strangest thing standing can mean, because the next entry is not a surface. It's a boundary. The event horizon of a black hole is not a surface at all, but a mathematical line beyond which nothing can return. Standing exactly at that boundary, time itself would behave differently for you than for someone watching from a distance, stretching and compressing in ways that break intuition entirely. Take the mass of several suns, compress it down to a single infinitely small point, and you get a black hole, an object first predicted mathematically decades before the first indirect evidence confirmed one. No light, no reflection, no way to signal back to anyone watching. But the next black hole on this list is not small at all, and calling it a star would almost be an insult to the word. A supermassive black hole, like the one anchoring the center of our own galaxy, holds the mass of millions of suns within a single point. Imaged for the first time directly in 2019, and again with our own galaxy's version in 2022, these objects remain mostly quiet despite their scale, like something enormous choosing to stay still. Standing near its event horizon, the distortion of space would be so extreme that you could theoretically look sideways and see the back of your own head, light bent so completely it wraps around itself. But the largest ones make even this one look modest, and the scale from here only grows harder to comprehend. Ultramassive black holes push far beyond that scale, with some estimated to hold the mass of tens of billions of suns. One of the most extreme candidates identified through observation could swallow objects the size of small planets without any noticeable effect on its overall structure. If you assume gravity always behaves the same way, no matter how large the source becomes, this is where that assumption starts to break down. Because at this scale, the space around the object stops behaving like space at all. But there is one theoretical object that goes even further than mass alone, because it strips away the one thing every black hole is supposed to have. A naked singularity is a purely theoretical concept, a point of infinite density with no event horizon hiding it from view. If it exists, the rules of physics as we currently understand them would not just bend near it, they would stop applying altogether. We have never observed one, and many physicists argue the universe may not allow one to exist at all, hidden behind a boundary, specifically so its full effects never reach observers like us. Standing near something like this would not be dangerous in the way heat or gravity is dangerous. It would be dangerous, because the very laws that describe danger might not hold anymore. No formula, no prediction, no way to know what standing there would even mean. That is where this list has to end, at the edge of what physics can even describe, standing on the last surface any of us could imagine and still call a place. If you made it through every one of these, from the dim light of a red dwarf to a point where the rules themselves may not apply, you already understand more about the universe than most people ever will. If you are not ready to leave these strange places just yet, there is a full playlist waiting for you. One star, one boundary, one impossible surface at a time.